Welcome to Mathematics and Data Science. I'm Barton Poulson, and we're going to talk about how mathematics matters for data science. Now, you may be saying to yourself, why math? And computers can do it. I don't need to do it. And really, fundamentally, I don't need math. I'm just here to do my work. Well, I'm here to tell you, no, you need math. That is, if you want to be a data scientist, and I assume that you do. So we're going to talk about some of the basic elements of mathematics, really at a conceptual level, and how they apply to data science. There are a few ways that math really matters to data science. Number one, it allows you to know which procedures to use and why, so you can answer your questions in a way that's the most informative and most useful. Two, if you have a good understanding of math, then you know what to do when things don't work right, that you get impossible values or things won't compute. And that makes a huge difference. And then three, an interesting thing is that some mathematical procedures are easier and quicker to do by hand than by actually firing up the computer. And so for all three of these reasons, it's helpful to have at least a grounding in mathematics if you're going to do work in data science. Now, probably the most important thing to start with is algebra. And there are three kinds of algebra that we want to mention. The first is elementary algebra. That's the regular x plus y. Then there's linear or matrix algebra, which looks more complex, but is conceptually simpler and is used by computers to actually do the calculations. And then finally, I'm going to mention systems of linear equations where you have multiple equations simultaneously that you're trying to solve. Now, there's more math than just algebra. A few other things that I'm going to cover in this course. A little bit of calculus. A little bit of big O or order, which has to do with the speed or the complexity of operations. A little bit of probability theory. And a little bit of Bayes or Bayes' theorem, which is used for getting posterior probabilities and changes the way that you interpret the results of an analysis. And for the purposes of this course, I'm going to demonstrate the procedures by hand. Of course, you would use software to do this in the real world, but we're dealing with simple problems at conceptual levels. And really the most important thing to remember is, even though a lot of people get put off by math, really, you can do it. And so, in sum, let's say these three things about math. First off, you do need some math to do good data science. It helps you diagnose problems. It helps you choose the right procedures. And interestingly, you can do a lot of it by hand, or you can use software, computers to do the calculations as well. As we begin our discussion of the role of mathematics in data science, we'll of course begin with the foundational elements. And in data science, nothing is more foundational than elementary algebra. Now, I'd like to begin this with really just a little bit of history. In case you're not aware, the first book on algebra was written in 820 by Muhammad ibn Musa al-Khwarizmi, and it was called The Compendious Book on Calculation by Completion and Balancing. Actually, it was called this, which if you transliterate that comes out to this, but look at this word right here. That's the algebra, which means restoration. In any case, that's where it comes from. And for our concerns, there are several kinds of algebra that we're going to talk about. There's elementary algebra, there's linear algebra, and there are systems of linear equations. We'll talk about each of those in different videos. But to put it into context, let's take an example here of salaries. Now, this is actually based on real data from a survey of the salary of people employed in data science. And to give a simple version of it, the salary was equal to a constant. That's sort of an average value that everybody started with. And to that, you added years, and then you added some measure of bargaining skills and how many hours they worked per week. And that gave you a prediction, but because it wasn't exact, there's also some error to throw into it to get to the precise value that each person has. Now, if you want to abbreviate this, you can write it kind of like this: S plus C plus Y plus B plus H plus E. Although it's more common to write it symbolically like this. And let's go through this equation very quickly. The first thing we have is outcome. We call that Y, the variable Y, for person I. I stands for each case in our observations. So here's outcome Y for person I. This letter right here is a Greek beta, and it represents the intercept or the average. That's why it has a 0, because we don't multiply it times anything. But right next to it, we have the coefficient for variable 1. So beta, which means a coefficient, sub 1 for the first variable. And then we have variable 1, and then x1 means variable 1, and then the I means it's the score on that variable for person I, whoever we're talking about. And then we do the same thing for variables 2 and 3, and then at the end, we have little epsilon here with an I for the error term for person I, which says how far off the prediction was from their actual score. Now I'm going to run through some of these procedures and we'll see how they can be applied to data science. But for right now, let's just say this in sum. First off, algebra is vital to data science. It allows you to combine multiple scores, get a single outcome, do a lot of other manipulations. And really, the calculations are easy for one case at a time, especially when you're doing it by hand. The next step in mathematics for data science foundations is to look at linear algebra, or an extension of elementary algebra. And depending on your background, you may know this by another name, and I like to think welcome to the matrix, because it's also known as matrix algebra, because we're dealing with matrices. Now, let's go back to an example I gave in the last video about salary, where salary is equal to a constant plus years plus bargaining plus hours plus error. Okay, that's a way to write it out in words. And if you want to put it in symbolic form, it's going to look like this. Now, before we get started with matrix algebra, we need to talk about a few new words. Maybe you're familiar with them already. The first is scalar, and this means a single number. And then a vector is a single row or a single column of numbers that can be treated as like a collection. That usually means a variable. And then finally, a matrix consists of many rows and columns, sort of a big rectangle of numbers. The plural of that, by the way, is matrices. And the thing to remember is that machines love matrices. Now, let's take a look at a very simple example of this. Here is a very basic representation of matrix algebra or linear algebra, where we're showing data on 2 people on 4 variables. So over here on the left, we have the outcomes for cases 1 and 2, our people 1 and 2. And you put them in the square brackets to indicate that it's a vector or a matrix. Here on the far left, it's a vector because it's a single column of values. Next to that is a matrix that has here on the top the scores for case 1, which I've written as x's. x1 is for variable 1, x2 is for variable 2. And the second subscript is to indicate that it's for person 1. Below that are the scores for case 2, the second person. And then over here in another vertical column are the regression coefficients. That's a beta there that we're using. And then finally, we've got a tiny little vector here at the end, which contains the error terms for cases 1 and 2. Now, even though you would not do this by hand, it's kind of helpful to run through the procedure. So I'm going to show it to you by hand. And we're going to take 2 fictional people. This will be fictional person number 1. We'll call her Sophie. We'll say that she's 28 years old, and we'll say that she has good bargaining skills, a 4 on a scale of 5, and that she works 50 hours a week, and that her salary is $118,000. Our second fictional person, we'll call him Lars, and we'll say that he's 34 years old and he has moderate bargaining skills, 3 out of 5, works 35 hours per week and has a salary of $84,000. And so if we're trying to look at salaries, we can go back to our matrix representation that we had here with our variables indicated with their Latin and sometimes Greek symbols. And we're going to replace those variables with actual numbers so we can get the salary for Sophie, our first person. So let me plug in the numbers here. And let's start with the result here. Sophie's salary is $118,000. And here's how these numbers all add up to get that. The first thing here is the intercept, and we just multiply that times 1. So that's sort of the starting point. And then we get this number 10, which actually has to do with years over 18. She's 28, so that's 10 years over 18. We multiply each year by 1395. Next is bargaining skills. She's got a 4 out of 5, and for each step up, you get $5,900. By the way, these are real coefficients from study of survey of salary of data scientists. And then finally, hours per week. For each hour, you get $382. Now, we can add those up and we can get a predicted value for her, but it's a little low. It's 30,000 low, which you may say, well, that's really messed up. Well, that's because there's like 40 variables in the equation, including she might be the owner. And if she's the owner, yeah, she's going to make a lot more. And then we do a similar thing for the second case. But what's neat about matrix algebra or linear algebra is that you can use matrix notation. And this means the same stuff. And what we have here are these bolded variables that stand in for entire vectors or matrices. So for instance, this Y, a bold Y, stands for the vector of outcome scores. This bolded X is the entire matrix of values that each person has on each variable. This bolded beta is all of the regression coefficients. And then this bolded epsilon is the entire vector of error terms. And so it's really super compact way of representing the entire collection of data and coefficients that you use in predicting values. So in sum, let's say this. First off, computers use matrices. They like to do linear algebra to solve problems. And it's conceptually simpler because you can put it all there in this tight formation. In fact, it's a very compact notation and it allows you to manipulate entire collections of numbers pretty easily. And that's the major benefit of learning a little bit about linear or matrix algebra. Our next step in mathematics for data science foundations is systems of linear equations. And maybe you're familiar with this, but maybe you're not. And the idea here is there are times when you actually have many unknowns and you're trying to solve for all of them simultaneously. And what makes this really tricky is a lot of these are interlocked. Specifically, that means X depends on Y, but at the same time, Y depends on X. What's funny about this is it's actually pretty easy to solve these by hand, and you can also use linear matrix algebra to do it. So let's take a little example here of sales. Let's imagine that you've got a company and you've sold 1,000 iPhone cases so they're not running around naked like in this picture. And that some of the cases sold for $20 and others sold for $5. You made a total of $5,900. And so the question is, how many were sold at each price? Now, hopefully you were keeping your records, but you can also calculate it from this little bit of information. And to show you, I'm going to do it by hand. Now, we're going to start with this. We know that sales, the two price points, X and Y, add up to 1,000 total cases sold. And for revenue, we know that if you multiply a certain number times $20 and another number times $5, that it all adds up to $5,900. Between the two of those, we can figure out the rest. Let's start with sales. Now, what I'm going to do is I'm going to try to isolate the values, and I'm going to do that by putting in this minus Y on both sides. And then I can take that and I can subtract it. So I'm left with X is equal to 1,000 minus Y. Normally you solve for Y, but I solve for X. You'll see why in just a second. Then we go to revenue. And we know from earlier that our sales at these two price points add up to $5,900 total. Well, what we're going to do is we're going to take this X that's right here and we're going to replace it with the equation we just got, which is 1,000 minus Y. Then we multiply that through and we get 20,000 minus 20Y plus 5Y equals 5,900. Well, we can subtract these two because they're on the same thing. So 20Y, and we get 15Y. And then we subtract 20,000 from both sides. So there it is right there on the left. And that disappears. And then I get it over on the right side. And I do the math there and I get minus $14,100. Well, then I divide both sides by negative $15. And when we do that, we get Y is equal to 940. Okay, so that's one of our values for sales. So let's go back to sales. We have X plus Y equals 1,000. We take the value that we just got, 940, we stick that into the equation, and then we can solve for X. Just subtract 940 from each side. There we go. We get X is equal to 60. So let's put it all together just to recap what happened. What this tells us is that 60 cases were sold at $20 each, and that 940 cases were sold $5 each. Now, what's interesting about this is you can also do this graphically. We're going to draw it. So I'm going to graph the two equations. Here are the original ones we had. This one predicts sales. This one gives price. The problem is these really aren't in the canonical form for creating graphs. That needs to be y equals something else. So we're going to solve both of these for y. We subtract x from both sides. There it is on the left. We subtract that, and then we have y is equal to minus x plus 1,000. That's something that we can graph. Then we do the same thing for price. Let's divide by 5 all the way through. That gets rid of that. And then we've got this 4x, and then let's subtract 4x from each side. And what we're left with is minus 4x plus 1180. That's also something that we can graph. So here's the first line. This indicates cases sold. It originally said x plus y equals 1,000, but we rearranged it to y is equal to minus x plus 1,000. And so that's the line we have here. And then we have another line which indicates earnings. And this one was originally written as $20 times x plus $5 times y equals $5,900 total. We rearrange that to y equals minus 4x plus 1180. That's the equation for the line. And then the solution is right here at the intersection. There's our intersection, and it's at 60 on the number of cases sold at $20 and 940 on the number of cases sold at $5. And that also represents the solution of these joint equations. And so it's a graphical way of solving a system of linear equations. So in sum, systems of linear equations allow us to balance several unknowns and find the unique solution. And in many cases, it's easy to solve by hand. And it's really easy with linear algebra when you use software to do it at the same time. As we continue our discussion of mathematics and data science and the foundational principles, the next thing we want to talk about is calculus. And I'm going to give a little more history right here. The reason I'm showing you pictures of stones is because the word calculus is Latin for stone, as in a stone used for tallying, where people would actually have a little bag of stones and they would move them and they would use it to count sheep or whatever. And the system of calculus was formalized in the 1600s simultaneously, independently by Isaac Newton and Gottfried Wilhelm Leibniz. And there are three reasons why calculus is important for data science. Number one, it's the basis of most of the procedures that we do. Things like least squares regression and probability distributions, they use calculus in getting those answers. Second one is if you're studying anything that changes over time. So if you're measuring quantities or rates that change over time, then you have to use calculus. Calculus is used in finding the maxima and the minima of functions, especially when you're optimizing, which is something I'll show you separately. Also, it's important to keep in mind there are two kinds of calculus. The first is differential calculus, which talks about rates of change at a specific time. It's also known as the calculus of change. The second kind of calculus is integral calculus, and this is where you're trying to calculate the quantity of something at a specific time given the rate of change. And it's also known as the calculus of accumulation. So let's take a look at how this works, and we're going to focus on differential calculus. So I'm going to graph an equation here. I'm going to do y is equal to x squared, a very simple one, but it's a curve, which makes it harder to calculate things like the slope. So let's take a point here that's at -2. That's my little red dot. We have it x is equal to -2. And because y is equal to x squared, if we want to get the y value, all we got to do is take that -2 and square it, and that gives us 4. So that's pretty easy. So the coordinates for that red point are -2 on x and +4 on y. Here's a harder question. What is the slope of the curve at that exact point? Well, it's actually a little tricky because the curve is always curvy and there's no flat part on it. But we can get the answer by getting the derivative of the function. Now, there are several different ways of writing this. I'm using the one that's easiest to type. And let's start by this. What we're going to do is the n here. And that is the squared part. So we had x squared. And you see that same n turns into the squared. And then we come over here and we put that same value 2 in right there. And we put the 2 in right here. And then we can do a little bit of subtraction. 2 minus 1 is 1. And truthfully, you can just ignore that and you get 2x. That is the derivative. So what we have here is the derivative of x squared is 2x. That means the slope at any given point of the curve is 2x. So let's go back to what we had a moment ago. Here's our curve. Here's our point at x minus 2. And so the slope is equal to 2x. Well, we put in the minus 2 and we multiply it and we get minus 4. So that is the slope at this exact point on the curve. Okay. What if we choose a different point? Let's say we come over here to x is equal to 3. Well, the slope is equal to 2x. So that's 2 times 3 is equal to 6. Great. And on the other hand, you might be saying to yourself, and why do I care about this? There's a reason that this is important. And what it is that you can use these procedures to optimize decisions. And if that seems a little too abstract to you, that means you can use them to make more money. And I'm going to demonstrate that in the next video. But for right now, in sum, let's say this. Calculus is vital to practical data science. It's the foundation of statistics, and it forms the core that's needed for doing optimization. In our discussion of mathematics and data science foundations, the last thing I want to talk about right here is calculus and how it relates to optimization. I like to think of this, in other words, as the place where math meets reality, or it meets Manhattan or something. Now, if you remember this graph I made in the last video, y is equal to x squared. That shows this curve here, and we have the derivative that the slope can be given by 2x. And so when x is equal to 3, the slope is equal to 6. Fine. And this is where this comes into play. Calculus makes it possible to find values that maximize or minimize outcomes. And if you want to make something a little more concrete out of this, let's think of an example here. By the way, that's Cupid and Psyche. Let's talk about pricing for online dating. Let's assume you've created a dating service and you want to figure out how much can you charge for it that will maximize your revenue. So let's get a few hypothetical parameters involved. First off, let's say that subscriptions, annual subscriptions currently cost $500 a year, and you can charge that for a dating service. And let's say you sell 180 new subscriptions every week. On the other hand, based on your previous experience manipulating prices around, you have some data that suggests that for each $5 you discount from the price of $500, you will get 3 more sales. Also, because it's an online service, let's just make our lives a little simpler right now and assume that there is no increase in overhead. It's not really how it works, but we'll do it for now. And I'm actually going to show you how to do all this by hand. Now, let's go back to price first. We have this $500 is the current annual subscription price. And you're going to subtract $5 for each unit of discount. That's what I'm giving D. So 1 discount is $5, 2 discounts is $10, and so on. And then we have a little bit of data about sales, that you're currently selling 180 new subscriptions per week, and that you will add 3 more for each unit of discount that you give. So what we're going to do here is we're going to find sales as a function of price. Now, to do that, the first thing we have to do is get the y-intercept. So we have price here. $500 is the current annual subscription price minus $5 times D. And what we're going to do is we're going to get the y-intercept by solving when does this equal 0. Okay, well, we take the 500, we subtract that from both sides, and then we end up with minus 5D is equal to minus 500. Divide both sides by minus 5, and we're left with D is equal to 100. That is, when D is equal to 100, X is 0, and that tells us how we can get the y-intercept. But to get that, we have to substitute this value into sales. So we take D is equal to 100, and the intercept is equal to 180 plus 3. 180 is the number of new subscriptions per week. And then we take the 3, and then we multiply that times our 100. So 180 times 3 times 100 is equal to 300. Add those together, and you get 480. And that is the y-intercept in our equation. So when we've discounted sort of price to 0, when price is 0, then the expected sales is 480. Of course, that's not going to happen in reality, but it's necessary for finding the slope of the line. And so now let's get the slope. The slope is equal to the change in y on the y-axis divided by the change in x. One way we can get this is by looking at sales. We get our 180 new subscriptions per week plus 3 for each unit of discount. And we take our information on price, $500 per year minus $5 for each unit of discount. And then we take these, the 3D and the 5D, and those will give us the slope. So it's plus 3 divided by minus 5, and that's just minus 0.6. And so that is the slope of the line. The slope is equal to minus 0.6. And so what we have from this is sales as a function of price, where sales is equal to 480, because that's the y-intercept when x is equal to 0, when price is 0, minus 0.6 times price. So this isn't the final thing. Now what we have to do is we turn this into revenue. So there's another stage to this. Now revenue is equal to sales times the price. How many things did you sell and how much did it cost? Well, we can substitute in some information here. If we take sales and we put it in as a function of price, because we just calculated that a moment ago, we get this, and then we do a little bit of multiplication, and then we get that revenue is equal to 480 times the price minus 0.6 times the square of the price. Okay, that's a lot of stuff going on there. What we're going to do now is we're going to get the derivative. That's the calculus that we talked about. Well, the derivative of 480 in the price, where price is sort of the x, the derivative is simply 480. And the minus 0.6 times the square of the price, well, that's very similar to the thing we did with the curve. And what we end up with is 0.6 times 2 is equal to 1.2 times the price. This is the derivative of the original equation. We can solve that for 0 now. And just in case you're wondering, why do we solve it for 0? Because that is going to give us the place when y is at a maximum. Now, we had a minus squared, so we have to invert the shape. And we're trying to look for this value right here when it's at the very tippy top of the curve, because that will indicate maximum revenue. Okay, so what we're going to do is we're going to solve for 0. Let's go back to our equation here. We want to find out when is that equal to 0. Well, we subtract 480 from each side. There we go. And we divide by minus 1.2 on each side. And this is our price for maximum revenue. So we've been charging $500 a week, but this says we'll have more total income if we charge $400 instead. And if you want to find out how many sales we can get, currently we have 480. And if you want to know what the sales volume is going to be for that, well, you take the 480, which is the hypothetical y-intercept when the price is 0, but then we put in our actual price of 400, multiply that, we get 240, do the subtraction, and we get 240 total. So that would be 240 new subscriptions per week. So let's compare this. The current revenue is 180 new subscriptions per week at $500 per year. And that means that our current revenue is $90,000 per year. I know it sounds really good, but we can do better than that, because the formula for maximum revenue is 240 times 400. When you multiply those, you get 96,000. And so the improvement is just the ratio of those two. 96,000 divided by 90,000 is equal to 1.07. And what that means is a 7% increase. And anybody would be thrilled to get a 7% increase in their business simply by changing the price and increasing the overall revenue. So let's summarize what we found here. If you lower the cost by 20%, go from $500 per year to $400 per year, assuming all of our other information is correct, then you can increase sales by 33%. That's more than the 20 that you had. And that increases total revenue by 7%. And so we can optimize the price to get the maximum total revenue. And it has to do with this little bit of calculus and the derivative of a function. So in sum, calculus can be used to find the minima and the maxima of functions, including prices. It allows for optimization, and that in turn allows you to make better business decisions. Our next topic in mathematics and data principles is something called Big O. And if you're wondering what Big O is all about, well, it is about time. Or you can think of it as how long does it take to do a particular operation? It's the speed of the operation. If you want to be really precise, the growth rate of a function, how much more it requires as you add elements, is called its order. That's why it's Big O. That's for order. And Big O gives the rate of how things grow as the number of elements grows. And what's funny is there can be really surprising differences. Let me show you how it works with a few different kinds of growth rates, or Big O. First off, there's the ones that I say are sort of just on the spot. You can get stuff done right away. The simplest one is O1, and that is a constant order, and that's something that takes the same amount of time no matter what. You can send out an email to 10,000 people, just hit one button. It's done. The number of elements, the number of people, the number of operations, it just takes the same amount of time. Up from that is logarithmic, where you take the number of operations, you get the logarithm of that, and you see it's increased, but it's really only a small increase, and it tapers off really quickly. So an example is finding an item in a sorted array. Not a big deal. Next one up from that. Now, this looks like a big change, but in the grand schemes, it's not a big change. This is a linear function where each operation takes the same unit of time. And so if you have 50 operations, it takes 50 units of time. If you're storing 50 things, it takes 50 units of space. So find an item in an unsorted list. It's usually going to be linear time. Then we have the functions where I say, you better just pack a lunch because it's going to take a little while. The best example of this is what's called log linear. That's where you take the number of items and you multiply that number times the log of the items. And an example of this is something called a fast Fourier transform, which is used for dealing, for instance, with sound or anything that's over time. You can see it takes a lot longer. If you got 30 elements, you're way up there at the top of this particular chart at 100 units of time or 100 units of space, or however you want to put it. And it looks like a lot, but really that's nothing compared to the next set where I say, you're just going to be camping out. You might as well go home. That includes something like the quadratic. You square the number of elements. And you see how that just kind of shoots straight up. That's quadratic growth. And so multiplying two n-digit numbers. So if you're multiplying two numbers that each have 10 digits, it's going to take you that long. It's going to take a long time. Even more extreme is this one. This is the exponential 2 raised to the power of the number of items you have. You'll see, by the way, the red line here doesn't even go to the top. That's because the graphing software that I'm using doesn't draw it when it goes above my upper limit there. So it kind of cuts it off. But this is a really demanding kind of thing. It's, for instance, finding an exact solution to what's called the traveling salesman problem using dynamic programming. That's an example of exponential rate of growth. And then one more I want to mention, which is sort of catastrophic, is factorial. You take the number of elements and you raise that to the exclamation point factorial. And you see that one cuts off really soon because it basically goes straight up. You have any number of elements of any size, it's going to be hugely demanding. And for instance, if you're familiar with the traveling salesman problem, that's trying to find a solution through the brute force search. It just takes an extraordinary amount of time. And so, before something like that's done, you're probably just going to, turn to stone and wish you never even started. The other thing to know about this is not only do some things take longer than others, some of these methods, some functions are more variable than others. So for instance, if you're working with data that you want to sort, there are different kinds of sorts or sorting methods. So for instance, there's something called an insertion sort. And what you find is that on its best day, it's linear. It's O of n. That's not bad. On the other hand, the average is quadratic, and that's a huge difference between the two. Selection sorts, on the other hand, the best is quadratic and the average is quadratic. It's always consistent. So it's kind of funny. It takes a long time, but at least you know how long it's going to take versus the variability of something like an insertion sort. So in sum, let me say a few things about Big O. Number one, you need to know that certain functions or procedures vary in speed. And the same thing applies to making demands on a computer's memory or storage space or whatever. They vary in their demands. Also, some of them are inconsistent. Some of them are really efficient sometimes and really slow or really difficult the others. Probably the most important thing here is to be aware of the demands of what you're doing, that you can't, for instance, just run through every single possible solution, or your company will be dead before you get an answer. So be mindful of that so you can use your time well and get the insight you need in the time that you need it. A really important element of the mathematics and data science, and one of its foundational principles, is probability. Now, one of the things that probability comes in intuitively for a lot of people is something like rolling dice or looking at sports outcomes. And really the fundamental question, what are the odds of something? That gets at the heart of probability. Now, let's take a look at some of the basic principles. We got our friend Albert Einstein here to explain things. The principles of probability work this way. Probabilities range from 0 to 1. That's like 0% to 100% chance. When you put P, that stands for probability, and then in parentheses, here A, that means the probability of whatever in parentheses. So PA means the probability of A, and then P of B is the probability of B. When you take all of the probabilities together, you get what's called the probability space, and that's why we have S. And it all adds up to 1 because you've now covered 100% of the possibilities. Also, you can talk about the complement. The tilde here is used to say probability of not A is equal to 1 minus the probability of A, because those have to add up. So let's take a look at something also about conditional probabilities, which is really important in statistics. A conditional probability is the probability of something if something else is true. You write it this way, the probability of, and that vertical line is called a pipe, and it's read as assuming that or given that. So you can read this as probability of A given B is the probability of A occurring if B is true. And so you can say, for instance, what's the probability if something's orange? What's the probability that's a carrot given in this picture? Now, the place where this comes in really important for a lot of people is the probabilities of type 1 and type 2 errors in hypothesis testing, which we'll mention at some other point. But I do want to say a few things about arithmetic with probabilities, because it doesn't always work the way that people think it will. Let's start by talking about adding probabilities. Let's say you have two events A and B. And let's say you want to find the probability of either one of those events. So that's like adding the probabilities of the two events. Well, it's kind of easy. You take the probability of event A and you add the probability of event B. However, you may have to subtract something. You may have to subtract this little piece because maybe there is some overlap between the two of them. On the other hand, if A and B are disjoint, which means they never occur together, then that's equal to 0. And then you can, subtract 0, which is you get back to the original probabilities. But let's take a really easy example of this. I've created my super simple sample space. I have 10 shapes. I got 5 squares on the top, 5 circles on the bottom. I've got a couple of red shapes on the right side. Let's say we want to find the probability of a square or a red shape. So we are adding the probabilities, but we have to adjust for the overlap between the two. Well, here's our squares on top. 5 out of the 10 are squares. And over here on the right, we have 2 red shapes, 2 out of 10. So let's go back to our formula here and let's change a little bit, change the A and the B to S and R for square and red. Now we can start this way. Let's get the probability that something is a square. Well, we go back to our probability space. You see we have 5 squares out of 10 shapes total. So we do 5 over 10, that reduces to 0.5. Okay, next up, the probability of something red in our sample space. Well, we have 10 shapes total. 2 of them on the far right are red. So that's 2 over 10. And you do the division, you get 0.2. Now the trick is the overlap between these two categories. Do we have anything that is both square and red? Because we don't want to count that twice. So we have to subtract it. So let's go back to our sample space. And we're looking for something that is square. There's the squares on top, and there's the things that are red on the side. And you see they overlap. And this is our little overlapping red square. So there's one shape that meets both of those, 1 out of 10. So we come back here, we do 1 out of 10, that reduces to 0.1. And then we just do the addition and subtraction here. 0.5 plus 0.2 minus 0.1 gets us 0.6. And so what that means is there's a 60% chance of an object being square or red. And you can look at it right here. We got 6 shapes outlined now. And so that's the visual interpretation that lines up with the mathematical one we just did. Now let's talk about multiplication for probabilities. Now the idea here is you want to get what are called joint probabilities, or the probability of two things occurring together simultaneously. And what you need to do here is you need to multiply the probabilities. And we can say probability of A and B, because we're asking about A and B occurring together, a joint occurrence. And it's equal to the probability of A times the probability of B. That's easy. But you do have to expand it just a little bit, because you again have the problem of things overlapping a little bit. And so you actually need to expand it to a conditional probability. The probability of B given A. Again, that's the vertical pipe there. On the other hand, if A and B are independent, if they never co-occur, or B is no more likely to occur if A happens, then it just reduces to the probability of B and you get your slightly simpler equation. But let's go and take a look at our sample space right here. So we've got our 10 shapes, 5 of each kind, and then 2 that are red. And we're going to look at originally the probability of something being square or red. Now we're going to look at the probability of it being square and red. Now I know we can eyeball this one really easy, but let's run through the math. The first thing we need to do is get the ones that are square. There's those 5 on the top, and the ones that are red, and there's those 2 on the right. In terms of the ones that are both square and red, yeah, obviously there's just this one red square at the top right. But let's do the numbers here. We change our formula to be SNR for square and red. We get the probability of square. Again, that's those 5 out of 10. So we would do 5 out of 10, reduce this to 0.5. And then we need the probability of red given that it's a square. So we only need to look at the squares here. There's the squares, 5 of them, and 1 of them is red. So that's 1 over 5. That reduces to 0.2. You multiply those two numbers, 0.5 times 0.2, and what you get is 0.1, or a 10% chance, or 10% of our total sample space is red squares. And you come back and you look at it, you say, yeah, there's 1 out of 10. So that just confirms what we were able to do intuitively. So that's our short presentation on probabilities. And in sum, what do we get out of that? Number one, probability, it's not always intuitive. And also the idea that conditional values can help in a lot of situations, but they may not work the way you expect them to. And really, the arithmetic of probability can surprise people. So pay attention when you're working with it so you can get a more accurate conclusion in your own calculations. Let's finish our discussion of mathematics and data science and the basic principles by looking at something called Bayes' theorem. And if you're familiar with regular probability inferential testing, you can think about Bayes' theorem as the flip side of the coin. You can also think of it in terms of intersections. So for instance, standard inferential tests and calculations give you the probability of the data, that's our D, given the hypothesis. So if you assume a null hypothesis is true, this will give you the probability of the data arising by chance. The trick is most people actually want the opposite of that. They want the probability of the hypothesis given the data. And unfortunately, those two things can be very different in many circumstances. On the other hand, there's a way of dealing with it. Bayes does it. And this is our guy right here, the Reverend Thomas Bayes, an 18th century English minister and statistician. And he developed a method of getting what are called posterior probabilities that uses prior probabilities and test information, or things like base rates, how common is something overall, to get the posterior or after the fact probability. Here's the general recipe to how this works. You start with the probability of the data given the hypothesis, which is what you get from the likelihood of the data. You also get that from a standard inferential test. To that, you need to add the probability of the hypothesis or the cause being true. That's called the prior, or the prior probability. To that, you also add the probability of D, the probability of the data. That's called the marginal probability. And then you combine those in a special way to get the probability of the hypothesis given the data, or the posterior probability. Now, if you want to write it as an equation, you can write it in words like this. Posterior is equal to likelihood times prior divided by marginal. You can also write it in symbols like this. Probability of H given D, probability of the hypothesis given the data, that's the posterior probability, is equal to the probability of the data given the hypothesis, that's the likelihood, multiplied by the probability of the hypothesis and divided by the probability of the data overall. But this is a lot easier if we look at a visual version of it. So let's go to this example here. Let's say we have a square here that represents 100% of all people, and we're looking at a medical condition. And what we're going to say here is that we've got this group up here that represents people who have a disease. So that's a portion of all people. And then what we say is we've got a test, and people with the disease, 90% of them will test positive. So they're marked in red. Now it does mean that over here on the far left, we have people with the disease who test negative. That's 10%. Those are our false negatives. And so if the test catches 90% of the people who have the disease, that's good, right? Well, let's look at it this way. Let me ask a basic question. If a person tests positive for disease, then what is the probability that they really have the disease? And if you want a hint, I'm going to give you one. It's not 90%. Here's how it goes. So this is the information I gave you before, and we've got 90% of the people who have the disease. That's a conditional probability. They test positive. But what about the other people, the people in the big white area below of all people? Well, we're going to need to look at them and see if any of them ever test positive. Do we ever get false positives? And with any test, you are going to get false positives. And so let's say our people without the disease, and that 90% of them test negative the way they should. But that of the people who don't have the disease, 10% of them test positive. Those are false positives. And so if you really want to answer the question, if you test positive, do you have the disease? Here's what you need. What you need is the number of people with the disease who test positive divided by all people who test positive. Let's look at it this way. So here's our information. We've got 29.7% of all people are in this darker red box. Those are the people who have the disease and test positive. All right, that's good. And then we have 6.7% of the entire group. That's the people without the disease who test positive. So we want to do the probability of the disease. So we have what percentage have the disease and test positive, and then divide that by all people who test positive. And that bottom part's made up of two things. That's made up of the people who have the disease and test positive and the people who don't have the disease and test positive. Now we can take our numbers and start plugging them in. Those who have the disease and test positive, that's 29.7% of the total population of everybody. We can also put that number right here. That's fine. But we also need to look at the percentage that do not have the disease and test positive of the total population. That's 6.7%. So we just need to rearrange. We add those two numbers on the bottom. We get 36.4. And we do a little bit of division. And the number we get is 81.6%. Here's what that means. A positive test result still means only a probability of 81.6% of having the disease. So the test is advertised as having 90% accuracy. Well, if you test positive, there's really only an 82% chance that you have the disease. Now, that's not a really big difference, but consider this. What if the numbers change? For instance, what if the probability of the disease changes? Here's what we originally had. Let's move it around a little bit. And let's make the disease much less common. And so now what we do is we're going to have 4.5% of all people are people who have the disease and test positive. And then because there's a larger number of people who don't have the disease, we're going to have a relatively larger proportion of false positives. Again, compared to the entire population, it's going to be 9.5% of everybody. So we're going to go back to our formula here in words and start plugging in numbers. We get 4.5% right there and right there. And then we add in our other number, the false positives. That's 9.5%. Well, we rearrange and we start adding things up. That's 14%. And when we divide that, we get 32.1%. Here's what that number means. That means a positive test result, so you get a positive on the test, now means that you have a probability of only 32.1% of having the disease. That's 2/3 less than the advertised accuracy of 90%. And in case you can't tell, that's a really big difference. And that is why Bayes' theorem matters, because it answers the question that people want, and the answer can be dramatically different depending on the base rate of the thing that you're talking about. And so, in sum, we can say this. Bayes' theorem allows you to answer the right question people really want to know. What's the probability that I have the disease? As opposed to what's the probability of getting a positive if I have the disease? They want to know whether they have the disease. Now to do this, and this is the big trick, you need prior probabilities. You need to know how common the disease is. You need to know how many people get positive test results overall. But if you can get that information and run them through, it can change your answers and really the emotional significance of what you're dealing with dramatically. Let's wrap up our discussion of mathematics and data science and the data principles and talk about some of the next steps, things that you can do afterwards. Probably the most important thing is you may have learned about math a long time ago, but now it's a good time to dig out some of those books and to go over some of the principles that you've used before. The idea here is that a little math can go a long way in data science. So things like algebra and things like calculus and things like big O and probability. All of those are important in data science, and it's helpful to have at least a working understanding of each. You don't have to know everything, but you do need to understand the principles of your procedures that you select when you're doing your projects. There are two reasons for that, very generally speaking. First, you need to know if a procedure will actually answer your question. Does it give you the outcome that you need? Will it give you the insight that you need? Second, really critical, you need to know what to do when things go wrong. Things don't always work out. Numbers don't add up. You get impossible results or things just aren't responding. You need to know enough about the procedure and enough about the mathematics behind it that you can diagnose the problem and respond appropriately. And to repeat myself once again, no matter what you're working on in data science, no matter what tool you're using, what procedure you're doing, focus on your goal. And in case you can't remember that, your goal is meaning. Your goal is always meaning.